Hello everyone and welcome to today's theory prep video. Today we'll be talking about how to read a definition. And just to explain a little bit, this week we'll focus much more on skills and less on content. Some of the skills that are really important for 121 and 124 are being able to read complicated definitions and understand not only what they mean mathematically, but what they also mean intuitively. And secondly, you're going to want to be able to understand much longer proofs, which is what the other video will cover. And so we'll just sort of give examples, do sort of lots of different types of problems that have long proofs or long definitions, and that'll help you build those skills. Let's get into it. So the definition that we're going to look at today is the definition of a Turing machine, which is a pretty important one in computer science, but a really complicated one. So if you want to pause the video and just take a look and try to read through it here, it at first looks really complicated. A Turing machine with k-states, an alphabet, sigma, is represented by a transition function that maps Cartesian product. It just gets really, really complicated. And to be honest, it's pretty hard to understand at first pass. So we're going to go ahead and first talk about one, how should you go through a definition? And then two, we'll do that for this definition. Great. So first, how to read a definition. So whenever you see a definition, and definitions are like the fundamental building block of mathematics. So understanding definitions is even more important than understanding theorems, which is even more important than understanding the proof of the theorem. So definitions are supposed to capture ideas, right? Last week or a couple of weeks ago, we talked about injectivity, which is supposed to capture the idea of cardinalities or the idea of functions sort of mapping elements to unique things. And so the first thing that you should ask is what is the motivation for this definition, right? Because if there's no reason to define something, then we need not define it, right? You could define a set maybe I'll call the special numbers is the set 2, 3, and 5. But why is that important? If I can't give you a reason that's important, then nobody really needs to remember that definition. Second is you want to ask, what is the intuitive idea that I'm trying to capture? And this sort of will be often sort of interlinked with the motivation. So again, going back to surjection, right? In a surjection, you're trying to capture that a function covers everything. Or in an undirected graph, you're trying to capture symmetric relationships between different entities. And so you want to make sure you really understand that, because when you're reading the definition, you want to make sure that the math corresponds to that intuition. So the third step is it's good to try and think, if I was the person defining this, how would I define it? And chances are a lot of times when you define it, it'll actually look really similar to what the final definition is. So that can make it easier to read through it, because you're like, oh, I know what this is because I just wrote something very similar. If not, it might be different. You might sort of think differently than the person who wrote the definition, but it's still a really useful exercise to think about how should we construct definitions. So step number 4 is you should read the definition. And while you're reading, try to understand how the mathematical structures, how each line of the proof or each line of definition or each set in the definition corresponds to some part of the intuitive idea that you're trying to capture. And it'll definitely take a couple of reads, especially with complex definitions, to really understand what is the definition trying to capture. But as you're going through, you should be asking yourself at every step, what does this part mean? Is this line necessary? And why do we have to restrict the set in this way? Or every single part of the definition there should be a reason for. And you should really be interrogating as you go through, asking yourself, what part of the intuition does this correspond to? Why doesn't it capture this intuition if we didn't have this condition here? And then lastly, it can often be really helpful to try some simple examples to build better understanding. If you're trying to do step 4 and you've read through the definition a couple times, you don't really understand it, sometimes it can actually be good to skip to step 5, try an example, and that'll give you a little bit of a better picture. All right, so let's talk about motivation and intuition. So the motivation for a Turing machine is a model of a computer. And we're computer scientists, so we probably should define a computer, right? If we want to ask questions like what is computable by a computer, then we need some sort of model of a computer so that we can actually prove that computers can compute things or can't compute things. So that's a pretty basic definition that we might need. And as a little bit of history, so originally, before we had these mechanical technological computers were, that was a job. It was a profession that somebody had, and you would just compute things by hand. And so we, when they sort of defined the Turing machine, they defined it to capture this intuition, right? Because that's what the computer was. A computer was just like a person who looks at some stuff on paper and then writes out some results. And so what we're going to try to do today is we're going to try and capture the behavior that a human computer is doing in math, right? Because what we're trying to do is we're trying to capture the intuition of a computer in math. So we'll take this example of a person computing stuff out and see if we can create an algebraic structure that models the same thing. Okay, so let's take a short example to sort of build on this. So how would you compute the equation below? So if I was here, and let's just put every single symbol in its own box. And if I was computing this, first, there's like no information in my head, right? And then, so the first thing that I do is I look at this first symbol on the left, right? And I'm like, 3, okay. So I have a 3, and then I'm like, I should read the next symbol to the right. So now, in my head, I have 3, and now I've read plus. So now I update what's in my head, and now, like in my head, right, I sort of have like 3 plus here. And then I move again to the right, because I'm like, I still need to know what I'm trying to add, right? And then I see a 2, and I'm like, okay, 3. Then now in my head, I have 3 plus 2, and I'm like, I should still keep moving to the right, right? Because like, if this was like 3 plus 2 and the next box said 7, then it would be like 3 plus 27. So I keep moving, and then I see, oh, that's blank. There's nothing there. So now, like, I know the state 3 plus 2, like in my head, that just corresponds to 5. So what I'm gonna do is I'm basically, now I'm gonna just go back, I'm gonna erase this. So I'm gonna move left, I'm gonna erase this, and still like in my head, the state is 5, right? Or I'm thinking, okay, I just need to return 5, and I'm gonna get rid of this, right? And I'm gonna keep moving left, and then I'm gonna get rid of this, and I'm just gonna replace it with 5, right? That's how I would do this problem at like a really granular level. I think something as simple as addition, it's like, you just like see it and you know it, but like really you're parsing all the information, and as you're parsing the information, you're sort of updating what's going on in your head, and then eventually, based on sort of like what's in your head, you can like write different things down on the paper, right? And so that's what our structure is going to try and capture. So at each step, we moved right, left, or we stayed in the same, or we could have stayed in the same position. We didn't, but I guess, like if you were computing something and, you were to like erase some symbol and write some other symbol there, you may want to like stay in that position. But we can move, and then we changed what was in our head, right? Like from 3 to 3 plus 3. And then we also potentially wrote something on the tape, right? So, and the tape being sort of like this series of like 3 plus 2, just like if you imagine like a series of infinite boxes, right? That's sort of like your scratch paper, right, that you have to work with. You could just sort of assume you have infinite scratch paper to keep writing stuff on. And to make this concrete, let's say this like little dot is me, right? And let's keep track of both like where we're moving, what we're storing internally in our head, which we'll call our state, and what we're writing on the tape, right? So at first, there's like nothing in my head. It's just blank, right, when I start the problem. And so now I read a 3. I decide to move right because I need to keep reading more information. So now this is me. I'm looking at the plus, and now in my head, I have the string like 3, right? And so now I see a plus, and I'm like, I need to keep reading for more information. So I move right. So now this is me, and now in my head, the state is 3 plus, and now I'm looking at this 2. And then I decide to move right again because I see a 2. So now the state in my head will be 3 plus 2, and I'll move right again. And so now this is me. I'm looking at a blank thing, and in my head I have 3 plus 2. And now I'm like, okay, it's blank. That means I finished reading the equation. I know 3 plus 2 corresponds to 5. So now I'm going to update my internal state to 5, and I'm gonna move left, right? And I'm just going to keep erasing everything until I get to the beginning of the paper, and then I'm just going to write down 5, right? So now I've moved left, so now this is me. Still, the internal state of my head is 5, and now I'm looking at this 2. And now I'm going to move left, so I'm going to be here, but first I'm going to write like blank. I'm going to erase this 2. So now there's nothing in this square, right? So still, in my head, the state is 5. Now I'm looking at this plus. And again, I'm like, okay, I'm not at the edge of the paper, so I'm going to erase this as well, and I'm going to move left again. So now, this is me. Now I'm here. at the 3. And so I still have 5 as the state in my head. And I'm like, okay, I'm going to cross out this 3. And I'm just going to write 5 in its place. And now I'm going to like tell my supervisor, like I'm done. I finished the computation, right? And so we might call that halting. We'll say instead of returning like move right or left at that step, we'll just return halt. I'm done. This is my answer. And so as we kind of discussed a little bit, we can model storing stuff in our head as some number k. And when we put any like natural number in these hard brackets, what we mean is, so k is just the set. It's shorthand for the set like 0, 1, 2, all the way up to k minus 1. So just the set of k different numbers. And we can model like the memory in our head, right? What we're thinking about in our head or the state as some like finite number, because they only have so much like memory. You can only remember so many things in your head. So so that seems like appropriate to limit it, as opposed to saying like it can be any natural number, because a human computer can only store like so much information in their head. So it's fair to have the state capped out at some point. So let's create a model of us. If this is me right here, right, and I'm the computer, then what do I get? At every state, what I'm getting in, or at every point in time, right, when I'm like moving back and forth on this tape, doing the computation, I'm getting in a state, right, because I'm getting in whatever I previously had in my head. I'm also getting in something from the tape because I'm looking at something on the tape. Then I'm getting out a new state that I'm going to be in, like a new thing I'm going to remember. I'm also putting out like a direction, and that direction we can say, like we could write it as like L for left, R for right, S for stay in the same place, or H for halt. And then I'm also writing something out to the tape. And in these earlier steps, right, when I was like reading 2 and just moving to the right, you could say like I'm always writing something to tape. But in these cases where I just like moved and didn't really actually write something to tape, I could have just been writing whatever was on the tape to it again. So that's sort of like an important detail there. We could just say we always write something to the tape, and when we don't want to, we just write whatever was already there. Great. All right, so now we're ready to actually take a look at this definition. And as we discussed earlier, we're going to go through, and at every line, we're going to think, why did they do this? Why couldn't it have been done some way else? And how does this correspond to our intuition of how a human computer works? Another thing that you might keep in mind is sometimes you're going to like, when you're reading definitions, the first time you see the symbol, you might not completely understand it. But in those cases, probably just continuing to read the definition will eventually make it clear what that symbol is. So you don't have to do the interrogation the first time you read it through. The first couple times you read it through could just sort of be to get a sense of what stuff is. And then when you feel like you sort of know what's going on, then you can go and interrogate each of the symbols. So let's read through the definition like that. First, a Turing machine with k states and an alphabet sigma. So the states probably correspond to sort of like what's in our head, and it's not exactly clear what the alphabet is, but we'll just keep going, right, and hopefully we'll figure that out. Is represented by a transition function that maps a state in some element of the alphabet to a state some element of the alphabet, and L, R, S, or H. Okay, so that's all a little bit foggy. It's kind of unclear what this means, but we're going to keep going, and eventually we'll sort of start to understand it. And so for some input to the Turing machine, the output, M of X, is the result of doing the following process. So this is going to tell us how the Turing machine is going to work. So we initialize T, which seems to just be some sequence. So to be this triangle symbol, then X0 through Xn minus 1, so like the input bits of X, and then these other symbols. And now this sort of implies that T seems like it's our tape, right? It's our like scratch work. It's our like the infinite sequence that we're working on. And it seems like we put this symbol, this little triangle, like as the start, and then we put the actual information that we were working with. And then we put a bunch of these other symbols. So what are these other symbols afterwards? Well, if we think about our human computer example, we didn't actually write out all these. We just wrote through +2, but technically, since we're working on like an infinite number of spaces, you could say every single one of those other spaces is blank. So it seems like this symbol right here might just indicate blank. And so now, we didn't really understand what alphabet was when we saw it, but now it makes sense. Oh, alphabet is probably like the different things we can write down on the tape, right? So if we were doing like arithmetic, the alphabet might be like plus, times, some various like the digits, and parentheses. But now we sort of understand, the alphabet is like the different things that we can write down on the tape. And so that's how we initialize our tape. So our tape is basically, to begin with, it's just like how we had in this example. It's like the whatever x is, the statement of the problem, and then there's a start symbol, and there's everything else is blank. Great. So then we initialize I to 0 and S to 0. Okay, it's not exactly clear what S is, but I, it seems like, I, we don't really know what it is either yet. So we're initializing two variables to 0. So we're just going to remember that, and we're going to be like, we should probably come back to this. And now we're going to repeat the following process. So we're going to evaluate the transition function on S and T indexed at I. And now we start to think, now we might know what I is. I seems to be the point at which you index T, so it seems to be our position on the tape, right? So if like I is 0, then we're at start. If I is 1, then we'd be at the first position on the tape. And then S, coming back to our model of what we're doing, right? We take in something on the tape, and then we take in the state, and that seems to be like exactly what the transition function is doing here. So that implies that S is probably our state, right? And so basically what we're saying here is that we initialize I to 0. So that's saying we start at the first position on the tape. And then when we say S is equal to 0, we're just saying like we start in the 0th state, which seems like an appropriate thing to assume, right? You don't really know any information going into the problem. That's totally fine. And then it's going to spit out S prime, sigma prime, and D. And whenever you have like some letter and then some letter prime, usually it means like basically the same thing, but like another iteration or another version of it or something like that. But it lives in sort of like the same universe. It's kind of like the same type of object in computer science. And so we're going to set S equal to S prime. So basically our transition function spits out some new state, right, S prime, and then that becomes our new state. And then it looks like sigma here is this thing right here, or sigma prime is this thing right here, the new symbol that we're going to write to the tape, right? Because we're saying Ti equal to that sigma. And that leaves D as probably the direction that we're moving in. And actually in 3, we see that that's exactly what it is. If D equals R, then I goes to I plus 1. So that means that we're moving to the right. If D equals L, I goes to the maximum of I minus 1 and 0. And again, remember, whenever you see stuff in definitions, always make sure like it's clear. Like, why is there a maximum here? And it might not be evident the first couple times you read it through. The first time you're reading through the definition, you see something like this, you don't really understand it. It's okay, just kind of keep going until you really feel like you understand the idea of what a Turing machine is. But then once you've read it a couple times, you might realize, the reason we need a maximum here is because let's say I was equal to 0 and the Turing machine said move left. Well, we can't really move left. We don't have negative positions on the tape. So instead, we'll just stay at 0, and that's what the maximum ensures. Intuitively, you can think of this as like if you're a human computer and you're doing work and you get to the left-hand side of the paper, you can't move any farther left. So it's like the physical edge of the paper. Great. And if D equals S, that seems to be the stay symbol. We'll keep it the same. And finally, if D equals H, then we halt. And that's also the same as in our sort of human example, where that means we're done with the problem. And so what happens when we halt? Well, when we halt, then now the output of M is defined by the string Y that's obtained by concatenating all the symbols that are 0 and 1 in the positions T0 through Ti, where I is the final head position of the Turing machine. So that is to say, like, let's say, I don't know, the final output is like triangle, right? You leave the start symbol there, 1, 0, like, I don't know, maybe you have some symbol that's question mark in your output 0, and your Turing machine ends up here. Well, in that case, your output would be, you look at all this, and you just take the 1s and the 0s. So it'd be 1, 0, 0. And that makes sense. In most cases, probably what we can do is just like the Turing machine can go back to the beginning, write down the answer, and then and be like, this is my answer, right? And halt there. And that's exactly what happens intuitively in the human case. They just go back to the left-hand side of the paper, write their answer down, and then call their like supervisor or whatever. And it's like, I have finished the problem. So now we sort of see how the intuition for the Turing machine follows. And again, when you're reading through all of this, make sure you ask yourself, like, why is every single detail in here? Do I really understand it? For example, why do we need this triangle symbol? Like, why do we need a start symbol? Why couldn't we just, instead of having triangle x0, x1, why couldn't we just write x0 in the first space and just have no start symbol, right? The Turing machine, like you still started in state 0 and you started at index 0. Couldn't you just have that be indicative of the Turing machine being in that starting place? The answer is, like, technically, yes, you could do that, and you could sort of modify any Turing machine that under this definition to fit that definition. But it's just, in this case, it's sort of like syntactic sugar. It's equivalent definition, but it's just nicer to think about it with this triangle, because sometimes you're going to want a part of the process where the Turing machine is just like running back to the head of the tape, and then it's nice to be like, keep going back until you hit the triangle symbol. So in this case, the answer would be like, oh, it's kind of like syntactic sugar. But you should always be on the lookout for like things that look weird in proof or in definitions. And whenever you find stuff like that, interrogate it and make sure it makes sense. So now we want to do the last step. And if we go back to our how to read a definition, the last step is to try an example, and that will help us build some understanding. So we're going to do that step. And the example we're going to do is a palindrome. So we're going to write a Turing machine that on input binary string will return 1 if and only if it's a palindrome. In other words, if you have something like 1001, it'll return 1. If you had something like 1101, then it would return 0. And what alphabet will we use? Well, we'll use the alphabet which is 0, 1, empty, and triangle. And remember, in the definition, it has to include those 4 symbols, but it can include other stuff. It can be a superset of that. So in particular, we're going to use this X symbol, and it'll become clear what the X symbol means in the proof, but for now you can just think about it as meaning like match. So how's it going to work? There are 12 states. You can read them if you want, but I think the easiest way to understand it is just to sort of start reading how the transition function works. And let's do a concrete example here. So we'll do this on the example 1001, and that will really help us see what each of the parts are doing. So remember, we initialize a Turing machine, and for example, like working through this example is already helping us understand like what this first step really does, because now we have to do this step. We have to initialize the tape. We initialize it to triangle 1001, and then a bunch of these empty symbols, right, et cetera, on forever. So M is going to start here. It's going to start in the start position, and it's going to move right looking for a 0 or a 1. If it hits the empty symbol before a 0 or a 1, it's just going to go to output 1. And I'll explain exactly how output 1 works, but right now just think of it as that means it's just going to successfully output 1. And that makes sense, right? Because the only way that it's going to hit an empty symbol first is if the initial tape looks like this, in which case the input string must have been empty, which is a palindrome. So that checks out. And if it hits a 0 or 1, so in this case it's going to hit a 1, it's going to enter right 0 or right 1 respectively. So in this case, it'll enter state right 1. And first, it's going to write an X on the tape at that point. So it's going to erase this one. And now our tape is going to look like an X in that position. And then it's going to continue to move right until it hits either the empty symbol or the X. And so in this case, it'll keep moving right until it gets to this point. And once it hits that, it's going to enter look for 1. If it was in state right 0, then it would enter look for 0. But since it's in look right 1, it'll enter look for 1. And it's going to make one left move. So now it's going to be here, and it's going to check to make sure that this bit is 1. Since if this bit was 0, if that was incorrect, then it would just go into the mode output 0, which similarly output 1 will just output 0. That makes sense, because if this was a 0, it wouldn't be a palindrome, because it wouldn't be matching. In particular, the string 1000 is not a palindrome. And if B is correct, instead it'll erase this, it'll write an X in its place, and then it changes to state return. And return is just going to move left until it hits something that's not a 0 or 1. So in this case, it would go here until it gets to this, and it's going to then change back to the start symbol, or the start state. And so now we see what this is doing. Basically, we're grabbing the first element, then we're checking to make sure that the last element is the same thing. We're going to erase those both as match symbols. Then we're going to go to the second element. We're going to check to make sure that's the same as the second to last element. And this will maintain and make sure that we have a palindrome. And so that's sort of the intuition behind what the Turing machine is doing. For completeness, we should explain also how output B works. So for output B, we're just going to go left until we hit the start symbol. So again, this is an example of how that syntactic sugar is helping us out here. Then we're going to go right and change state to B blank. So for concreteness, let's just say we're in output 1. So now we've changed to state 1 blank. So now we're here, and we're in state 1 blank. And in state 1 blank, what we're going to do is we are just going to write 1 to the tape. So now instead of whatever was there, there's going to be a 1, and we're going to move 1 to the right. And we're going to switch to state blank stop. And in state blank stop, Basically, it's just going to change whatever symbol's on the tape to a blank, and then it's going to return halt. And when it returns halt, then this last step of the definition tells us how we get our output. Well, we look at everything up to the point where the tape is. So in that case, it's just the first 3 parts of the tape. And we only look at ones and zeros, in which case this will be 1. Similarly, if this had been output 0 that we had been running, then this would have been written as a 0. So the output would have been given as a 0 as well. So we see that works. And so now we see this is sort of an example of how a Turing machine can calculate the palindrome function. And so it's starting to help us build intuition for how can Turing machines model things that we actually care about.